Good morning. Myself, Dr. A.N. Basugade, Professor and Head Department of Statistics, Gopal Krishna Gokhale College, Kolhapur. Today we are going to deal with the testing of hypothesis 2, and that too a part 3. In part 2, we have studied the two chi-square test. One is chi-square test of testing population variance, and second one is testing of goodness of fit. Now we are going to deal with the third test of chi-square test. So that is chi-square test of independence of two attributes. So as you know, the attribute means what? It is a qualitative characteristics which cannot be measured but which can be marked by the presence or absence of a certain characteristic is called as the attribute. For example, honesty we can't measure, intelligence, then blindness, nationality. So these are the some attributes which we cannot the quantities which cannot be measured but which can be marked by their presence or absence. So there may be many real life situations where attributes are used. For example, a person who is a smoker may be associated with the diseases like lung cancer. So whether there is any association or not, so that can be, or whether they are independent of each other. So these are the two attributes, smoking and disease. So they are the two attributes. So whether they are independent or related with one another, that we have to test with the help of this chi-square test of independence of the attributes. So second example is there may be association between level of education and marital adjustments. So these are the two attributes, education level and adjustment in married life. So is there any association, or they are independent? That can be tested with the help of chi-square test of independence of attribute. So first we will go for the chi-square test for m by n contingency table. Let A and B be the two attributes where A is divided into m classes as the A1, A2, AM, and B will be divided in n classes as B1, B2, Bn. Let AI equal to number of atoms having characteristic A in ith class, and Bj is number of atoms having characteristics of B in jth class. So and AIBJ is the common observations in A as well as which are satisfying A as well as category B or characteristic B. Just like honesty and intelligence. Suppose A is honesty, B is intelligence, then AIBJ means what? A person who are intelligent as well as the honest, they can be kept in the this AIBJ. So number of atoms possessing characteristic in ith class of A and jth class of B. Then the m by n contingency table can be represented as this one. So we have taken in the columns as B1, B2, Bj and Bn, n columns and m rows, A1, A2, AI and AM. So the common occurrence will be given as AIB, A1, B1, A2, A1, B2 and so on, A1, Bj and so on. So this total will be written as capital A1 bracketed. Bracketed means the number of atoms belonging to the first class A1. So in A1 class there are total will be some, these middle totals will be 2, 3, 5 like that way, and last total will be 50. Means what? In class A, the persons possessing the characteristic A will have the total of 50. Like that way we are having the A total to the column side, last A1, A2, A3 bracketed means the number of atoms in that particular class, and here in column wise bracketed B1, bracketed B2 will imply that the frequency of that B1 class or the number of atoms belonging to the B1 class, B2 class, Bj class and so on. And addition of these Bjs and addition of these AIs will give you the total number of observations under study. So that will be capital N. Now here summation AI equal to summation Bj, and that is also equal to sum of all the intermediate cell frequencies. So that will be double summation AI Bj One summation is over I, other summation is over j, and that is equal to n. We want to test whether the two attributes a and b are independent or not. So therefore our test hypothesis will be h0 such that two attributes a and b are independent, and h1 is they are dependent. It is known that if a and b are independent, it is known result in attributes. In last year we have studied the attributes, and there we have studied it as if a and b are independent, then ai into bj is equal to a bracketed ai into bracketed bj divided by n. So cell frequency ai bj can be obtained if they are independent, then ai into bj cell frequency total frequencies divided by n is the relation between the a and b when they are independent. The expected frequency can be obtained using this relation. So therefore E means expected frequency of AIBJ. AIBJ, they are the observed frequency, ith row, jth column. So OIJ are the AIBJ. But expected of AIBJ will be the bracketed AI into bracketed BJ divided by N. So that will be the expected using the since because we are assuming it as a independency. So to test the above hypothesis, the test statistics is given by chi-square calculated is double summation or I and j Oij minus Eij whole square divided by Eij has the chi-square distribution with m minus 1 into n minus 1 degrees. M means number of rows, n means number of columns. So that m minus 1 into n minus 1 degrees of freedom. Or if you simplify this square, that is Oij minus Eij whole square, then we are getting the relation as chi-square calculated is double summation over I and j Oij square divided by Eij minus the total frequency capital N has the chi-square with n minus 1 m minus 1 into n minus 1 degrees of freedom. If alpha is the level of significance and if chi-square calculated is greater than chi-square m minus 1 n minus 1 alpha, then we reject H0. Otherwise, we accept it at given level of significance. Now, the second case is not m by n, m will be 2 and n will be 2. That is 2 by 2 contingency table. So, there it is not necessary to go for the calculation of AIBJ. Directly, you can use this formula and you can obtain. If A and B are any two attributes having only two classes on each of them, then contingency table can be given as A has A1, A2, B has B1, B2 as the two classes. So there A1, B1 will be represented as A1, B2 is represented by B, that is the cell frequency common to A1, B1, A2, B2, and A2, B1 will be C and A2, B2 will be D. Their totals we have written as row wise total and column wise totals, and their total again will give you the total of frequency as a capital N. Here the test statistics for testing whether the two attributes A and B are independent or not, that can be given as the formula as chi-square calculated is equal to capital N into bracket AD minus BC whole square divided by all these sums product, that is A plus B into A plus C into B plus D into C plus D has the chi-square distribution with only 1 because m minus 1 n minus 1 m is 2 n is 2, there are 2 minus 1 into 2 minus 1 will be 1 degrees of freedom. So it will be has the chi-square distribution with 1 degrees of freedom. If alpha is the level of significance and if chi-square calculated is greater than chi-square with 1 degrees and level is alpha, then we reject H0. Otherwise, we accept it at given level of significance. So this is our first test of testing the independence of two attributes A and B. Now we'll go for the F test, the last test, that is F test, testing of equality of two population variances. In chi-square test, first chi-square test, what we have tested? We have tested the variance, but it is a single variance testing, that is sigma. H0 is your sigma equal to sigma square equal to sigma naught square. But here what we have to test? We have to test the H naught such that sigma 1 square equal to sigma. That means you have got the two populations and their variances are sigma 1 square and sigma 2 square respectively. Whether they are equal or not, or two samples came from the same population having same variances or not, that we have to test. So let x1 x2 dot 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 x1 xn1 and y1 y2 yn2 be the two independent random sample of size n1 and n2 drawn from the normal populations with means mu1 and mu2 and variances sigma 1 square and sigma 2 square respectively. Then x is normal with mean mu1 and variance sigma square I have written because the our hypothesis sigma 1 square equal to sigma 2 square is sigma, therefore I have written as sigma square, not sigma 1 square, but it is sigma square. And y is normal with mean mu2 and variance sigma square. Then as we have already defined, S1 square is sample mean squares are given by 1 upon n1 minus 1 summation xi minus x bar whole square, and S2 small s2 square, that is 1 upon n2 minus 1. It is mean square, not variance. So 1 upon n2 minus 1 summation yj minus y bar square as your sample mean square of y, sample mean square of x. Here we assume that s1 square is greater than s2 square. Therefore, it is known result. What are the known results? As already we have seen in the chi-square test, as ns square by sigma square is chi-square. But instead of s, we will use the sample mean square. Then we have already stated there also, that is n minus 1 s square by sigma square is chi-square. So here two samples are there, therefore I will write it as n1 minus 1 s1 square by sigma 1 square is chi-square with n1 minus 1 degrees of freedom, and n2 minus 1 s2 square by sigma 2 square is chi-square with n2 minus 1 degrees of freedom. So these are the known results we have to utilize. Our hypothesis for testing is what? H naught such that sigma 1 square equal to sigma 2 square versus H1 such that sigma 1 square not equal to sigma 2 square. So therefore the test statistics can be given as, by definition of Snedeker's F statistics, it is the ratio of two chi-square. Already we have mentioned this one, n1 minus 1 s1 square by sigma square as a chi-square, and n2 minus 1 s2 square by sigma 2 is also chi-square. Their degrees of freedom are different. So the ratio of two chi-square dividing with their degrees of freedom will follow the F distribution. So by definition of F statistics, we have got the test statistics F as F equal to n1 minus 1 s1 square by sigma square dividing with its degrees of freedom is n1 minus 1. This is one chi-square at the numerator, and the second chi-square is at the denominator, that is n2 minus 1 s2 square divided by sigma 2 square whole thing divided by n2 minus 1 has the F distribution with n1 minus 1 comma n2 minus 1 degrees of freedom. Now our hypothesis for testing is there is no significant difference in two variances, that is sigma 1 square equal to sigma 2 square versus sigma 1 square not equal. So that therefore it means equal means we denote it by sigma square. So on simplifications means what? At the numerator what is remained? n1 minus 1 at the numerator of this F statistics. n1 minus 1 n1 minus 1 at the numerator will get cancelled. n2 minus 1 n2 minus 1, those brackets will get cancelled at the denominator. You are remained with s1 square by sigma 1 square and whole thing divided by again s2 square by sigma 2 square. So but sigma 1 square and sigma 2 square are equal, they are denoted by sigma. So sigma 1 square is sigma square and sigma 2 square is again sigma square. So those division is again cancelled. So on simplifications what you are getting, will get it as under H naught F calculated will be s1 square by s2 square is F with n1 minus 1 n2 minus 1 degrees of freedom. If alpha is the level of significance and if F calculated is greater than F n1 minus 1 n2 minus 1 comma alpha by 2, then we reject H naught, otherwise we accept it at given level of significance. Now in this case we have assumed that the s1 square is greater than s2 square. If it is less, reverse is the case, that is If S1 square is less than S2 square, then F statistics will be reversed. That is S2 square divided by S1 square. This will follow a F, but degrees of freedom also changed. So N2 minus 1 comma N1 minus 1 degrees of freedom, and therefore the calculated value is also obtained using this formula, and the whole test procedure can be followed. So this is about the F statistics. So these are the things about the testing of hypothesis part 2. Three lectures we have seen. One is for t-test, other is for chi-square test of testing variance, testing the this goodness of it, and then the third one, in third lecture we have studied the chi-square test of independence of attribute and F tests. So this is regarding the testing of hypothesis. Thank you very much.